All right, so my first thing I'd like to do, first of all, thank you all for having me. I really appreciate it. But the first thing I'm going to do is correct my title because there's no such thing as glacial paleoseismology. I made that up in part to save space in this title slide. But this is basically my master's thesis. This is not the title of my master's thesis. It's just the title of this lecture. And really, the research summary is in the title. I'm studying the earthquakes, the paleoseismology, and the glacial history of the Strawberry Mountains, which are a surprisingly understudied yet scenically beautiful area of our wonderful state. And I'm going to start off with this fabulous map. This is the 2018 USGS seismic hazard map. This is the long-term forecast, which shows the probability of a 500-year recurrence interval of a damaging earthquake occurring everywhere in the United States. And Eastern Oregon is sort of this suspiciously green blob, which is a very low hazard level surrounded by sort of orange and yellow hazard areas. And my study area is right in the middle of that. And as you've gathered from the title, we've got earthquakes out here, but we don't measure them. We measure very few earthquakes in this area through seismometers in the USGS earthquake data catalog database. So the question I have about really all of Eastern Oregon is it actually less seismically active and hazardous as in the rest of the state, or are we missing stuff? And really our research is showing that we're missing stuff. And as Ian Maiden, the emeritus Dogami researcher, famously said to me personally, seismic hazard is a function of ignorance, and filling in these holes in ignorance is really something that gets me extremely excited, and I'm very passionate about that. So in late 2020, Ian Maiden sent me these. This is a digital elevation model, roughly the size of Rhode Island, that he emailed me. And on it, he had mapped a whole bunch of fault scarps. You can see them in these two inset images here, but in case you can't see them, I'll highlight them for you. And these are fantastic, very well-preserved fault scarps. And because they're so crisp and cut across all of these different aged landforms, we can infer that they are youthful. We can't say that they're young and active, but we can say that they're youthful. And until, that is, I did the research that I did last summer. And so the premise for this thesis, this research is the Strawberry Fault active in recent, that is Holocene time, the last 12,000 years? And if so, how many earthquakes have occurred on this fault structure and how frequently do they occur? And so I'm going to start in this with some background information on the local geology and plate tectonics. The Strawberry Mountains, which are located in Grant County in Eastern Oregon, a lovely remote part of the state. It's about a 7-hour drive from my front door here in Portland. And it's a lovely part of the state, very sparsely populated, where cows outnumber humans by about 3 to 1. And it's so rugged. There are mountains all throughout it. This is all part of the Blue Mountains Geophysical Province, which is composed of some of the oldest rocks in Oregon, and it's a lovely, remote, very rugged area. The Strawberry Mountains are a sub-range of this Blue Mountains area, and this is a geologic map I've got here, where the colors are broken down by age. This sort of yellowish color reflects the youngest sediments, that's Quaternary in age, less than 2 million years old. This sort of neutral gray is everything Miocene in age, so that is 18 million to 2 million. Is that right, Clark? Close enough. Okay. And then in orange, we have things that are a little bit older than that. That's the Tertiary period. So this includes things like the Clarno Formation, the John Day Formation. And then in green, we have even older than that. And these are Permian and Mesozoic rocks. So they're very old as far as Oregon is concerned. The largest rock unit in this green blob is the Canyon Mountain Ophiolite Complex, which is a chunk of oceanic crust that, for some reason that I can't quite wrap my head around, has thrust itself up into an arch shape, which underlies the Strawberry Mountains. And this is beautiful rocks. It's made up of basalt and serpentinite and peridotite rocks that really only we find deep underneath the ocean floor. And these are characterized by a high degree of deformation. They've been faulted and folded and squeezed and baked quite a lot in the last 350 million years. And then the rest of the Strawberry Range is this Strawberry Volcanics unit, which is a Miocene suite of andesites, rhyolites, and some basaltic andesites that takes up the same time period as the Columbia River basalts, but doesn't share very much in the way of geochemical relations. As the Yellowstone hotspot was upwelling underneath this part of the state, feeding the Monument Dike swarm to the north and the Steens Dike swarm to the south, everything in the middle was still getting really hot, and the Yellowstone plume melted the base of the crust, and so it produced a large suite of these andesite lava flows. And they're mostly undeformed, except by faulting along these black lines, which are pre-existing old bedrock faults. And the very top of the mountain, which you'll see in a couple of slides here, the Strawberry Fault is coeval with a system called the John Day Fault, which is one of the larger fault structures in the state of Oregon. And it's about 100 miles long from east to west. And in the Miocene, it allowed the Strawberry and Aldrich Mountains to uplift, and the John Day Valley to down drop. So we have sort of an anticline syncline system here with the John Day Fault cutting through the middle. And this is situated at a really interesting place in Oregon. To the south here, we have mostly northwest to southeast oriented faults. These are normal faults, part of the Basin and Range province, which fills up pretty much the southeast quarter of the state. And then to the north, we have this Blue Mountains region, which is treated by just about every single tectonic model as a solid, stable block. So we're located right here at the interface between these two extremely important provinces tectonically. That's in the wrong place. But this is a geologic map that I've been working on, and it sort of highlights just how many fault scarps there are. All of these red lines are fault scarps that I've mapped on the LiDAR. It's very high quality, very high resolution LiDAR mapping, which displays these fault scarps really, really well. And all these black dots you see are topographic profiles I've done across it. I'll come back to this later. This is what the Strawberry Peak looks like. This is the north slope of the mountains. And all of these planar lava flows, which were more or less horizontal when they erupted, are now back tilted between 10 and about 25 degrees to the south. So the whole mountain range kind of did this. And it's actually really easy to see. You don't need the LiDAR to look at it. You can stand anywhere in the mountains and you can see, it looks like the whole mountain range is leaning away from you. It's quite remarkable. And it highlights just how much vertical motion there's been along this fault system over the lifetime of the Strawberry Mountains. From the top of Strawberry Peak to the bottom of the John Day Valley, it's 6,000 feet. That's a lot of motion in the last, less than 10 million years. All right, back to tectonics. This is the widely accepted, agreed upon as the current tectonic models for the Pacific Northwest. We have the wonderful Whirlpool of Doom GPS vector for the state of Oregon and the Pacific Northwest. These are all GPS total stations which sit in one place and track the plate tectonic movement over time. And this is a derivative of actual GPS vectors as compared to stable North America. Now the continent's a little bit squishy, so there's some interpretation that goes into this GPS calculation, but they do show very little internal stress, internal shearing in this middle part of the state. My study area is right here, and you can see the John Day Valley. It's just a huge structure through the middle of the state. But even with this low displacement stress rate, you can still infer which way the rocks are getting strained and twisted. And in this area, we should expect right lateral horizontal and or reverse faulting, compression and strike slipping stress motion. But the Strawberry Fault isn't any of those. Yeah. So that's funky, right? It's intriguing. And it's one of the things that I really love about working in this area is that it doesn't make sense. Nothing here really makes sense. But before I can even get into thinking about why this fault is doing what it's doing, got to figure out how often the earthquakes occur, because that gives us an idea on how fast this fault moves over geologic time. But before I even get into the earthquakes, I'm going to talk about how the fault looks on the surface, because it's gorgeous. The surface expression of the Strawberry Fault is a normal fault that dips to the north with the north side down, with no detectable lateral component. Scarp heights, which reflect earthquake displacement on the surface, range between about 1¼ meters at Strawberry Creek and 2 3/4 meters here at Graham Creek. You can see the scarp cutting through here. These are some of the most beautiful glacial moraines I've ever seen in LiDAR. It's really fantastic. And the fault scarps that I've mapped total about 27 kilometers in length. And sort of statistical analyses into faults like this, done by Wisnowski and others in 2008, and many previous studies before that, suggest that a fault of this length could generate a magnitude 6.7 earthquake. Now that's bigger than the 1974 Silmar earthquake that devastated the northern Los Angeles basin. So that's a substantial earthquake, even though only 5,000 people live within range of this fault. It's still something that we should know about, right? And this is that topographic profile I was mentioning earlier, where we have the crest of the moraine here, and then the crest of the moraine down here. The Strawberry Fault cuts across that, and we have a 2.7 meter scarp, which when you're standing there, looks like this. It's pretty big once you know that it's there. But if you didn't know this was there, if you didn't have the LiDAR, like every single previous geologist who's been here didn't have, you wouldn't have any idea what this was. It's just a hill. You're in the woods. These are really dense old growth forests here on the north slope of the Strawberry Mountains. But once you start seeing stuff, things like this are all over the place. As are my field assistant, Kate Hedrick, and my thesis advisor, Ashley Stride here for scale. It's a big feature. We were really excited when we finally came across that. And speaking of this vertical separation like that, it varies along the length or the strike of the Strawberry Fault. And analyzing how it varies along the fault length can tell us relationships about scarp height and surface age, because if older surfaces are offset more, that means the fault's been active for a longer time than if an older surface was offset the same amount as a younger surface, because the old surfaces experienced more earthquakes, that means. And glacial moraines are great, and it's very nice, very convenient that we have them here, because we can absolutely date them using various exposure dating methods. We'll get into that a little bit later. But the thing I want to point out about this plot here, which shows the vertical displacement in meters here, and it's at its greatest here at the western end of the fault. I didn't include this area up here in this plot because excuse me, I wasn't able to get my feet on the ground up there, and I didn't want to just trust my LiDAR for that, even though I should, but I didn't because I just haven't seen that area. I'm not super familiar with it. So I kept it to the area that I've been to and that I know. And we see this sort of bimodal distribution. It's not really a distribution, it's just a plot, where we have these two peaks of older surfaces here on the ridge here, and over here at the western end of the fault strand on the front of the Strawberry Mountains. So it looks like, when we think about this empirically, most earthquakes on faults like this generally create between 3/4 and 1.5 meters of vertical separation on a fault of this size. So we get a very nice clustering of scarp heights in this 1 to 1.5 meter height interval. And then we have a whole bunch that are more than that. So these are definitely older surfaces, and that correlates to some of the geomorphic mapping I've done, just finding out what deposits are where and how old do they look based on how eroded they are or not eroded they are. But I lied about that plot, actually. I eliminated one of the most important data points, and that's this one here. This is a scarp that has a 15-meter scarp. Now, when everything else in the fault zone is sort of 1 to 3 A 15-meter scarp raises my eyebrows. And it lines up perfectly with this feature here. And this feature here is the largest and oldest glacial moraine in the Strawberry Mountains. And we only had a guess for how old it could have been when we first started looking into this. It could have been anywhere between 70,000 and 200,000 years old, which is much too great of a margin of error to be able to guess at what that might mean. But we have plenty of younger features, so we weren't too worried about that. And the glaciology was super important to figuring out the long-term activity and slip rate on the fault. The Strawberry Mountains were heavily glaciated in the previous ice ages, quite extensively in the most recent ice age. And the whole range, the north side and the south side, are just gouged with these massive U-shaped valleys. This is looking straight up Strawberry Canyon, which is one of the larger glacial basins. And on the LiDAR, it really is some of the best glacial morphology in the state. It's beautiful stuff. And once you see it on the LiDAR, it's very obvious and apparent on the ground, and you can find all sorts of interesting things, most of which I've unfortunately had to eliminate from this presentation. But there were several previous glacial studies that focused entirely on the morphology, how the glacial features look, how they've been preserved over time, and what kind of processes could have led them to be dropped where they are. These were done in 1995 and 1974. So that was a little bit before some of these high precision cosmogenic exposure ages methods were created. And the previous glacial studies did not have the LiDAR, so they missed quite a few glacial features as well. I've been working on revising their mapping for them. Speaking of LiDAR, this is that same Graham Creek moraine that I pointed out earlier. Lovely pair of moraines. We got the one high crest over here, and then there's another crest over here. And the fault scarp crosses both of them very well. And the LiDAR coverage really shows quite a number of different moraine crests inset within each individual sort of side of the drainage. On this one here, you can see very faintly at this zoomed out level, multiple little crests that extend out to the sides. And down here, there's more of them out to where the end of this glacier had moved around over time. But moraines that look like this are all over the place in the Strawberry Mountains, which is great. And because as I said earlier, they can be absolutely dated using cosmogenic radionuclide exposure dating, which we're analyzing how cosmic rays and stuff from space is interacting with, on the atomic level, with rocks here on the surface of the Earth, which is lovely if you're into sort of poetic scale differences, I guess. But cosmogenic radionuclide dating has been done on glacial features in the Cascade Mountains here around Mount Hood and in the south around Klamath Lake, and in the Wallowa Mountains around Wallowa Lake, but none has been done really elsewhere in the Blue Mountains. There were a few very old cosmogenic studies in Steens Mountain, but the data we collected here is the only data in a 160-kilometer circle. So that's filling in a huge gap in our understanding of glacial history. But all of these other ones, except for one, was done with the beryllium-10 method, which is the really common one that everyone uses and is generally what geologists mean when they say exposure dating. But that uses quartz. And as I said earlier, the Strawberry volcanics are made of andesite and basaltic andesite primarily, and there's no quartz in that. So we had to turn to the rather uncommon helium-3 method, which relies on pyroxene, which is a more primitive mineral crystal that contains iron and a few other heavier elements besides from silica and quartz. So the process for this, for really all glacial feature dating, is to locate boulders on or very near the crest of any given glacial moraine, like this one here, even though this one's a bit on the small side. The boulders need to be big enough so that you can be confident they haven't moved, they haven't been disturbed since the glacier dropped them there. And it's got to contain very visible pyroxene crystals and little to no vesicles. this rock in this photograph actually had just a few too many vesicles, but it's a great picture, so I threw it in anyway. And it takes a lot of work to hammer out the outermost layers of these boulders, which is usually done in waist-high brush looking like this. And it's this weathering rind that contains the disturbed pyroxene crystals, which contain helium-3, which we use to compare to all sorts of things. So I'll get into detail on that in a second. This is Kira McLean. She flew out to here from Vermont just to help out with this study. So I'm extremely thankful to her for her help. We ended up packing about 400 pounds of rock out of the strawberry wilderness, all permitted. This was all legal. Not everyone does that. And it cost about, it was very expensive to ship that across the country to Vermont, so they could process the samples. The basic sample preparation procedure is that the rock chips get crushed and sieved down to a very fine powder size. Then the individual pyroxene crystals get removed magnetically. They contain just enough iron that a very powerful magnet can pluck them out. These crystals then get washed with hydrofluoric acid, which is some particularly nasty stuff, to further isolate the crystals and keep the surfaces nice and pristine. Then those get shipped back across the country to Greg Balco at Berkeley Geological Center in California. And he fired a great big laser at each of these crystals for a spectroscopy analysis. I've illustrated here very crudely the principle of helium-3 dating. This galactic proton, which is sourced from supernovae out in the great expanse, that impacts generally with iron atoms, which physically knocks off, it spalls off this helium-3 isotope, this nucleus, and that creates argon, lithium, and a smattering of other products. And the lithium and the argon, I'm particularly pointing out here because those are also, actually everything on this chart is a product of radioactive decay. So the amount of all of these things you get in your rock is directly tied to the age of the rock. Now, in the Strawberry Mountains, you have a stack of lava flows that spans about 5 million years, and there's really no practical way to figure out where any of those came from, where each individual boulder came from. So we have to had to estimate a little bit. This particular volcanic setting exists elsewhere in the world, and that allows for a fairly good estimate of how much argon, lithium, and other stuff could contribute to the amount of helium trapped in the rock. So all of these helium-3 atoms are trapped in the crystal lattice of each individual phenocryst in the lava rock. I just think that's so cool. There's just helium atoms bouncing around inside there. That's really neat. So we use the age of the rock in geochemistry to estimate the ratio of radiogenic helium to cosmogenic helium. And overall, we sampled 3 glacial moraines last summer. Each one we selected because it was easy enough to get to, and because all 3 of these are of different ages. This one here, Slide Creek West, is very sharp crested, which suggests that it's very young. It has many sort of secondary glacial retreat features, lateral moraines, and some other features all along its length. So it's definitely very young. It's very well preserved. Slide Creek East is that really high, really old one. Look how rounded this is compared to Slide Creek West here. And then Graham Creek over here is the most beautiful glacial moraine set in the Strawberry Mountains. So we get 3 different aged moraines, each of which is crossed by the fault. And so once we get good ages for those, we have a snapshot of the fault's slip at 3 different points in time, which is great. That's very fortunate. That doesn't happen everywhere. And so we can correlate each of these moraine sets to a previous glacial advance, ideally. And here's the data from that. After all of these little crystals get blasted by the laser, I'm going to start with the Graham Creek moraine, which again is this one over here, because it's the first one I got back that worked really well. The Graham Creek moraine has these really nice tight distributions and has a great average age of about 21,300 years plus minus 600 before present. And once you've taken into account geochemistry and background helium, we're modeling that to be about 19,900 years old, which lines up perfectly to the well-established glacial chronology ages up in the Wallowa Mountains and in some parts of the Cascades, at least within the margin of error of those, which is great. I'm really excited about that. That little tiny Slide Creek West moraine produced no usable data, and it had roughly 100,000 year margin of error on either side of it. So that was too bad, but that's okay because we know it's the youngest one, regardless of what the data shows, just because of the way glacial features are younger as you go inside and down. So this is in line, as I said, with the Wallowa Lake glacial chronology. And with a tightly constrained age like this at 19,900 years and a very well understood scarp height here, 2.7 meters, we can take the scarp height and the age of the feature to get an average slip rate of 0.13 millimeters per year, plus or minus 1/100th of a millimeter, which is pretty, I'm happy with that margin of error personally, which is an expected tectonic setting, an expected average slip rate for somewhere this far inside the continent. It's great. Now, oh, train of thought left. What was that? That's that. That's nice. It's a nice feature. I like it. Now, the high old moraine Slide Creek East. I just got this data back. This was late June. I got this. So I have not been able to dig into it as much as I would like. But the preliminary data came back at 114,875 years before present, which is by far the oldest glacial feature I'm aware of that has been cosmogenically aged in Oregon and among the oldest in the Northwest. So that's very exciting, and it lines up with marine isotope stage 5D, if you know what that means. It's just a previous cold period where ocean isotopes were within a certain range that we've categorized it. And that's old. This is an old glaciation. This is 2 glaciations before the LGM. There was another one about 75,000 years ago, which is well preserved in the Cascades, and this one is older than that. Very exciting data. And once you incorporate the geochemistry and all those other things, get a modeled age about 92,000 years, which is between those two. But again, the margin of error supports it fitting really to either one, more likely the older glaciation. And that is the first pre-glacial, pre-LGM glacial feature in Oregon. I'm very proud, very excited about that. And this is that moraine with that 15 meter scarp height. And so when you take that into account, you get an average slip rate. Remember, 100,000 years, 0.16 millimeters per year. So within 300ths of a millimeter per year of the Grand Creek site, which is much more tightly constrained. So these slip rates, this average slip rate, the fault isn't creeping. Some faults do creep. They move very slowly, continuously over time. But most faults only move during earthquakes. So we get, if you take the amount of time between earthquakes and the amount the fault moves, you just average that to a very small millimeter number per year. So I'm not a glaciologist, but the morphological and the cosmogenic exposure analyses of these glacial features is providing a really good, really clear chronology of the glaciers in the north slope of the Strawberry Mountains, and they correlate very well to other inland alpine glacial systems across the Northwest. And I really hope that some other Northwest glacial and climatological researchers will be able to use some of this data to do things that I don't even really understand about glaciers. And this interpreted average slip rate for the Strawberry Fault going back nearly 100,000 years is not frequent in faults in this part of the country. So I'm very pleased with that. But I'm not a glaciologist. I'm an earthquake researcher. So I want to know how many earthquakes that takes. How many earthquakes are recorded on the Strawberry Fault? And how does that correlate to what we see with the scarps and other features on the surface? And that's a field called paleoseismology, which is just seismology, the study of earthquakes, but paleos, ancient. So this whole fault system, you get scarp heights generally ranging from 1.25 to 3, with occasional excursions bigger than that. How many earthquakes are recorded along the fault? And this Onion Creek site, which is a headline attraction of the upcoming Strawberry Mountains field trip in August, there's an area of ponded sediment high on the side of this canyon, which impounds just enough stuff coming off this hill that you have a flat impounded basin roughly the size of a football field. You can see the fault scarp here tracing its way facing uphill as it crosses this hill slope, and it creates a little dam in this small drainage that fills it up with sediment over time. And this is gold to a paleoseismic researcher. These 1.6 meter scarps are really well preserved. Here's Kira and lichen for scale. Kira's on the down thrown side, which, so here Kira is standing about here and lichen is standing about here in that picture. So the scarp is facing uphill here very clearly, and that works, and that's great because this area is a gentle enough environment that it preserves not only sediments and stratigraphy that correlate to individual earthquakes, but also those earthquake-related sediments are getting buried and preserved over time just by material washing off the hills above. So we use an auger core, which is a sort of a metal hand drill, and you just twist down into the ground, and it gives you about a 10-centimeter wide hole that lets you retrieve samples from further down, so you don't have to get in there with a pickaxe and a shovel. Though I did get permission to do exactly that later this year, which is very exciting. And these cores, if you do enough of them in a straight line, that allows you to create a cross section because you can correlate the same soils across linear space. So we found 5 main soil units in this area. We have a modern soil unit, then a slightly older soil unit that contains volcanic ash. Then we have a 10-centimeter thick layer of Mount Mazama ash throughout most of this area, that's a good sized ash layer for that far away from the volcano. And then we have this very dark buried soil. And then we have the glacial till beneath that. I'm not sure exactly how old this glacial till is, but I hope to look into that as this research season goes on. And after about 15 cores in one location, we came up with this cross section. I'll give you a second to digest this symphony of beige. Is that good? Digested? Okay, good. This is what we came up with for how all of these different things relate to each other. I'm going to start from the top here. So we've got this glacial till here. This is on the upthrown side of the fault. So every earthquake, this gets higher and this gets lower. Somewhere along probably a fault plane in this area is the most recent earthquake. That's the most recent surface displacement disruption at this location. And over time, that fault scarp, which was vertical initially, erodes and lays back, and it's called the free face. And that sort of buries itself as it diffuses over time. And you get gravel and small pebbles tapering away in a wedge from the fault scarp. That's called a colluvial wedge. That's something that just about every surface rupturing earthquake has. And it's great to be able to see that when you have it. And that grades seamlessly into the modern A horizon, which is very fluffy, it's that color. These are all the actual soil colors, by the way. And below that, it's actually a surprisingly stark color difference into the pre-existing soil, the soil that was active right before the most recent event. It's the same sort of ponded alluvium as the modern A horizon, but it contains enough Mazama ash inside it that it is a much lighter color. Right below that, we got this 10-centimeter layer of Mazama ash. Both of these units are folded against the fault plane, which means that they had to be there before the most recent earthquakes, that the earthquake could fold them. Again, fantastic, great stuff. Really excited when we found all this in the field. I was over the moon. Especially once we hit this buried soil. You pull up an auger core, you're in this brown, light, fluffy stuff, and then the soil is black. when you find something that stark of a difference, it's a big smile. And this buried soil is very fine, very clayey, it's very dark. And it also contains a tapering wedge of gravel and pebbles away from the fault scarp. And it was right in this area here, you know, you're doing most of these cores and you're getting down a half a meter, you know, 1.5 meters. And then we get one here that was, yes, you get a half meter up here, meter over here. And then suddenly this one was 170 centimeters deep. This core was, we had to get the extender out on the auger drill to be able to reach that far down. Very exciting stuff. And these all bottomed out in the glacial till on here. So we ended up with this really high quality cross section for auger coring, which is a notoriously low precision method because each auger core comes up sort of blended together. So you only get a 10 centimeter resolution on that. But it was good enough at this particular location to come up with a really nice looking cross section. And with the Mazama ash in the middle, that gives us an absolute age marker to compare to stuff above and stuff below. Very helpful, very useful in understanding the earthquake histories at this location. So each of these soils contain charcoal from ancient forest fires. And charcoal is wonderful because you can carbon date it. Carbon dating is pretty robust once you know what you're doing. So it's a very high precision, high confidence way to determine the age of an earthquake correlating unit of soil. You got to be real careful though, especially when you're auger coring, because right in the fault zone, the ground has been weakened by earthquakes. So it's really easy to dig down. So trees like to grow on there and groundhogs like to live in there. And they dig these very large holes and then they mix charcoal all throughout the soil column. So if you're taking charcoal from the fault zone, as I learned, you're getting into dangerous territory. But we looked through every single pile we pulled up. This is one of our smaller tarps full of sediment, I will point out. We picked out every piece of charcoal we could find in here. Ended up with dozens of them. They're all still down in the basement downstairs. And they look like this once you clean them up and you scrape the mud off, wash them off with some deionized water, deionized water, not deiodized water. And I didn't really know it at the time until I got the ages for these samples back, but you can learn a lot about a piece of charcoal just by looking at it. This is a millimeter scale on the side of it, so these are small. Most of them are pretty small, but this one is old. This one is old. And I know that because they're muddy, they're a little bit soft, they're rounded. Now this one was not old. This one is so not old that it came back on the spreadsheet of data as recent, which means it's less than 50 years old, but it came from 40 centimeters down on the ground. So these things happen in fault zones, especially when you're auger coring. If I dug a soil pit, which I will be doing later this year, I could see that this charcoal was located in an area that had been disturbed. So I wouldn't have picked it, but I did pick it and I spent $300 to get it tested and it didn't help me out. But all these dozens of charcoal samples I collected, I sent out 12. I had to very carefully pick 12 based on their location, which ones would be the most helpful. Ones that are right at the boundaries of units, so you can bracket the age of the units, or close to areas that have been offset by the fault, so you can figure out how old the offset is. It's a whole process to figure out, to weight different sample locations. So I submitted 12, but it was very expensive, and only 5 were usable for my earthquake history model, which is a little too few, but it's okay, it's good enough. 4 of those that didn't work were recent, less than 50 years old, and 3 were way too young to be where I found them from. Like I was finding charcoal much younger than the Mount Mazama eruption below the Mount Mazama ash layer. So that, I track that down to burrowing animals, or when you pull the auger core up, you can be knocking stuff in from higher up in the core. It's a fuzzy way of doing things, and it's you know, it's not the preferred method, but you take what you can get. And especially when you have to hike up as steep as a hill this was, I don't want to lug a shovel. But the data points we did get ended up being really good. This is from a system called OxCal, which is a calibration model made and produced by Oxford University, where you plug in your carbon-14 ages and it calibrates them. And then you plug in any events like earthquakes, which we had stratigraphic evidence for 2. We say there's an earthquake between these charcoal samples and these charcoal samples. And then there's the Mount Mazama eruption. We know how old that is. And then we know there's an earthquake right before that. And then we have the cosmogenic ages from the glacial features to give us sort of a lowermost bound. So we get a penultimate earthquake that's second most recent, between the last glacial maximum somewhere and the Mount Mazama eruption. So 7.6 thousand. And that's, you know, that's a big margin. It's 12,000 years is a fairly substantial margin of error for an earthquake that only lasts about a minute. But the most recent earthquake we got a good age for, and this was really exciting. It was dated between AD 210 and 1740, with which for really 4 samples on either side is a pretty tight grouping. I'm going to get more data this summer and really nail that down even closer, I hope. But with the stratigraphy at this site, we still get, you know, a total offset between the glacial till at the bottom and the glacial till at top at the site. And we still get an average slip rate of 0.13 millimeters per year. So that's great. We're getting similar average slip rates along the length of the fault. So that's great. That's a good sign that this data is robust and probably reflects truly on the fault, I like to think. So in summary, using this new glacial chronology in Paleoseismic, this is the first Paleoseismic study in the John Day Basin, we determined the Strawberry Fault is, yes, active in the Holocene. Therefore, by the USGS's own standards, it has to be considered as an active fault and therefore included in future earthquake hazard analyses. And, you know, that's important. Even if there's not 2 million people living in the John Day Valley, I think people deserve to live what they live, to know what they live with, right? I think that's important. But on a brighter note, it's just very exciting to get some of this first data of this area that I really hope will be useful to other researchers. The first glacial chronology ages in the Strawberry Mountains, the first pre-LGM ages in Oregon, and the first Paleoseismic study in the John Day Basin. This is all have good implications for future research. Earthquakes on this fault could reach about a magnitude 6.7, as I said earlier, and you know that would flatten Grant County pretty badly. But most interestingly for me, which is something that I didn't really think about before getting into this, is that the Strawberry Fault is reactivating that major ancient John Day system. Because the John Day Fault is so big and so old and so worn out, an earthquake can happen on it even though it doesn't fit the regional tectonic sort of stresses. It's so weak that reactivated faults can actually happen 65 degrees out of alignment either direction from the primary tectonic stresses, which is really, that's quite large. And that does more or less match with what we see. If I plot the primary stresses, which is a figure I'm just realizing now I didn't include in my slideshow here. If you take the primary stresses for this fault and draw an arc 65 degrees on either side of it, it fits the tectonic strain once you do that. So that's good. It does get me thinking though, how many other Strawberry Faults are there out in the Blue Mountains? We're just now beginning to get LIDAR for a huge swath of the state between Pendleton and John Day. Is that coming along, Clark? Do you know?
I've been out of it so long, I don't know.
Anyway, once we get the more new high quality LIDAR from this area, I have a suspicion we're going to find these things all over the place. And that gives me good job security. And plus it's fascinating. It's really interesting, especially considering how many tectonic models treat everything east of the Cascades as solid, stable, doesn't move. It moves. It moves and it's in lots of pieces. And that's very interesting. And, you know, food for thought for all of you tectonic modelers out there. With that, that's the conclusion of the talk. I'm going to give my acknowledgments to my field assistants, Kate Hedrick, Kira McLean, Lyson McHenry, Zoe Yeltley, Heather Feinberg, and Lisa Dunning. Yeah, my mom came and helped out for a few days, and she packed out more rock than any of us. Along with my research collaborators, Ashley Strigg, Will Amadon, and Greg Balco, who did the CRN dating. Martin Streck, another co-advisor, Ian Maiden, who is a font of information and handed me this project on a silver platter, and Willie Scott, a glacial guru from the 70s who turned me on to these earlier glaciations and gave me a good head start on figuring those out. So thank you to all of you if you happen to be watching. My grant funders slide seems to have vanished. So I received grant funding, the Geological Society of America, the Central Oregon Geoscience Society, who I hope is watching this in some capacity or another. Thank you. The Scion National Science Foundation, Natural Science Foundation, and the Mazamas, the mountain climbing group, gave me some money to do this glacial research. So thank you to all of you. And that's all I've got. I'll take any questions you have.
Looking at, I think it was LiDAR images, maybe also Google Earth, it looked to me like the John Day Valley had a V-shaped profile, which to me suggests it's still being, I don't know, it's fairly recently formed or it's still being actively eroded, but the profile is very shallow and broad.
Yes, in places. It's a surprisingly very complex area. It just sort of looks like it's a valley. Is this getting shared to Zoom, or do I need to do that annually?
It is.
Okay, good. Let's fly into Oregon here and take a look. So here's the John Day Valley, sticks out like a sore thumb right in the middle of the state. Get the roads off. And if you look at it from this altitude, the Strawberry Mountains, the Aldrich Mountains, and the Ochiko Mountains all form sort of a 100-mile-long arching alignment through the middle of the state, which most geologists interpret as it being an ancient sort of southernmost limb of the Yakima Fold and Thrust Belt, which is the result of everything south of there pushing up to the north and getting squished against Canada, more or less. But we look at the John Day Valley here, and in the western half, it's pretty sharp. It's pretty V-shaped at the bottom because the river is still actively incising down here, which it is doing as effectively as it is because it gets impounded by the Picture Gorge anticline. There we go. Which forms a lovely natural dam right in the middle of the valley. This is going to be one of the stops on the field trip in August because it is a fantastic example of what tectonics were doing before we hit the current sort of tectonic regime. And as we go to the east along it, right in here is where the John Day Fault starts to have a surface expression, not in terms of scarps or any kind of faulting features, but you get the various bedrocks are all jumbled. You get Columbia River basalts that are turned completely 90 degrees and are standing on their ends. And then you got Clarno-volcanics and much older rocks juxtaposed against each other. And this fault, it doesn't show up super well in the aerial imagery, but once you look at a geologic map, it is clear as day. And it runs all the way down pretty much the middle of the valley, underneath Main Street in John Day, zips up this gulch right here, and then disappears under the alluvial fans in the Rattlesnake Tuff, pretty much for good. And it doesn't, I've not been able to find any kind of surface expression until you hit the Strawberry Fault scarps. which on the satellite imagery aren't quite as impressive as on the LiDAR. Where is it? Here's that impounded basin here. Not really much to see, is it? But on the LiDAR, it looks fantastic. That's why LiDAR is so important. So it's right in here where the John Day Fault transitions from an east to west striking strike slip structure from the far past.
You can see the faults that start right along the base of the mountain.
Yeah, a little bit. This is older than the most recent features, but yeah, it goes right through here. You're right. Fantastic. And then the John Day Fault swings to the south and goes right up this canyon, which is the headwaters of the John Day River. And once it gets to this point, it is basically indistinguishable from the basin and range structures, which you get on either side of the Hayden Valley here, Logan Valley, or Summit Prairie over here. There's actually a whole strand of fault scarps along here, along the side of this slope from Summit Prairie to Crane Prairie. That's going to be the subject of a future summer, perhaps. Didn't quite get there last year or this year. But it really shows just how much is going on in these mountainous areas, these forested areas that are easy to skip over if you don't know what you're looking for. So yes, the John Day Valley is very interesting. To answer your question. Yeah, I think the broadness of the valley here at the end is probably a product of the more rapid uplifts, is my best guess. I don't know if the Strawberry Mountain part is uplifting faster, but you have a much broader alluvial plain there, which in the Basin and Range province means that one side is uplifting faster than the other.
I have a question. I was wondering more about the dating,
Mhm.
you spent all this time dating. What exactly were you dating? Just the surface of the glacier, any old place, or or did you have specific locations you were targeting and why?
So yes, I did have specific locations I was targeting. Whoops. Zoom in here.
I mean, yeah, I'm trying to get the whole.
Okay, so these glacial. Yeah. So we picked these three moraines to date. And the most important thing to date on these glacial moraines is the boulders right on the crest, right on the top. Because those have of the moraine, right where it crests out.
Okay.
And we picked these three because they reflect different ages. You go from the sharpest crest over here, then you get a sort of intermediate sharpness crest over here, and then you have this really broad, really wide crest on this one.
And so that gives you the age that the glacier was last active?
Yes.
Okay.
The idea is that hopefully the boulder you're selecting didn't get flipped over at some point,
Yeah.
or that it didn't get recycled, that it didn't get plucked from somewhere else where it was already getting sun exposure.
Right.
And I did get a couple of those,
Yeah.
but those are pretty easy to
So
see.
if you date a few rocks and they correlate, then you figure that you've got some good dates there for that.
Right.
Shoot for.
Yes. And generally, if they cluster as well as these ones have been, then you can feel good about it. The Slide Creek West moraine there did not look good. One of the rocks came back as 400,000 years old, which it wasn't.
Yeah. It had been somewhere else.
Came from somewhere else.
So if you have a fault scarp cutting that,
Mhm.
then you know that it was active since
Yes.
that glacier.
Fault
was in
scarp
place.
is younger than the glacier,
Yeah,
the glacial moraine.
okay,
And so as long as your boulders haven't moved,
yeah,
then you can get, in some cases, very tight bracketing of the age of the glacial feature,
okay.
which gives you a good place to compare to the fault scarp.
very non-technical question here, but why did you have to send samples for that helium-3 dating all the way to Vermont to be processed and all the way back to Berkeley?
Because he did it for free.
Oh,
It's very expensive. And that's his interest field. So he was able to pay for all the processing and all the analysis, basically out of his personal research funds.
Sorry, could we repeat the question?
Oh, yeah, the question was, why did I send the helium-3 samples to Vermont and then back? And the answer for that is he did it affordably because that's his interest field, and as a collaborator with myself and Ian and Ashley, this applies to the stuff he already spends his time and money researching. So I'm gathering his data so that he doesn't have to effectively. And then he handled all of the technical stuff for me, which is what science collaborators are for. And then we sent it back to Berkeley because he's the only guy in the US that does it.
We have some questions in the chat.
yeah, it's just coming up. So, Charlie's asking, where are the forces coming from to cause the fault movements over such a period of time?
That's a fantastic question. It's a fantastic question. And the best I can do is show you that map I already showed you, which is this one, or either one of these really. So if you picture the Northwest as these independent solid blocks that are all moving, sort of with respect to each other, starting from the south, I'll start from the north down. In the north, you have the Rocky Mountains, which they're not going anywhere fast. They're comparatively actually solid. We call it the backstop. And then everything south of here, the North Cascades and sort of southwest Washington, that's much younger, softer, squishier rock. So it finds it easier for it to fold and compress and fault. So this is getting shorter up here. And the Cascades here are more or less solid because they're all underlain by granite and other intrusives. And then the Coast Range in the valley here is underlain by Silesia, which is another comparatively solid big chunk of basalt and oceanic crust. And it's getting pushed up by the Sierra Nevada, Klamath Mountains. Everything in this area is very solid and getting pushed northward as part of the broader San Andreas fault style tectonics that we have on the West Coast. All of that contributes to the collapse of the basin range. It's best described as, I think, because this is getting pushed out. And so this has nowhere to go, but also out. So it's getting wider. So this zone here, what exactly is going on here? I don't know. We get basin and range style faulting. How often does that happen and how fast does it move? No idea. Hopefully we'll figure that out eventually. But in this part of the state, if you look at either of these maps, it's kind of in a no man's land. It doesn't look like there's anything obvious or apparent, certainly nothing like what's happening up here in the Olympic Mountains. So, oops, my first thought when I came upon these GPS vectors was, okay, that's basically noise. I'm not going to try and think about that. I'm not going to try and assign significance to something if I don't know, before I know that the fault is actually doing what we think it's doing. And now that we do know that the fault is doing what we thought it was doing, I can spitball a little bit. And I think that the relatively slow expansion of the northernmost basin range in this area is interacting with the more or less solid minimal strain rate part of the Blue Mountains in here, just enough to produce an earthquake every 10,000 years. Does that answer your question at all? No one has a good answer for that question. I sat at Brett's Club, a geomorphology conference in April with Ray Wells and Ian and Ashley and Andrew Miggs, which they're basically the big four tectonics people in the Northwest. And We talked about it for 3 days and just kept shrugging our shoulders and moved on with our lives. It's fascinating. I love it.
So a few more questions from the chat. Wes was asking, when in talking about the age of the various deposits, did you evaluate the outer core deposits on site, or did you have to analyze them back in a lab?
So we are estimating the soil unit ages, like the ponded alluvium or this top one or this buried soil based on the charcoal. The charcoal ages, you know, frankly, we're assuming, but with high confidence, that the ages of the charcoal pieces correlate to the age of the soil. Except for the Mazama ash. I mean, you know, if you're being super rigorous, you should send it off to a lab, which I did. But the waiting list is so slow on that that I'll be lucky if I get it back by the end of this year. And I sent it last year. I sent it this time last year. The volcanic chronology labs are quite backed up. But that's the only unit that is getting tested, I guess, directly. Because the Mazama ash, you melt it down, you do the chemistry on it. It's this volcano, it's this eruption that gets done all over the world. A lot of great technology in the Northwest. We're very lucky to have so many active volcanoes. But we determined it was Mazama ash because there's really nothing else it would be in this geomorphically fresh of an area. And there's also just no other volcanoes that have had that big of an eruption in the last 20,000 years or so in the Cascades. Does that answer your question, Wes?
Yeah, a little hard to, but let me have one more follow-up question from Wes, and then we'll get to you, Danny. Is that okay? Your newly revealed faults seem to be more east-west oriented than the usual northwest oriented, or am I missing something?
No, that's right. That's the whole premise of why this is such a significant fault, really. Yeah, when you look at it in particularly in this diagram, we're seeing reactivation inside this red square, which, you know, on that axis just doesn't really jive with the way it's moving or with the way the rest of the state is moving relative to it. So yes, you're right. It is anomalous and it's funky. And that's why I like it.
Yeah, on that last slide where it showed the fault zone, on those layers, I'm not quite clear. For example, the Mazama ash, where is the ash layer on the other side of the fault? Did it get displaced somewhere else?
Yeah, it would have been laid down up here. And since this is high, it's getting eroded away. So the ash that was here got washed down, and it's now, the bottom of Strawberry Creek is choked with Mazama ash. It's all over the place. We'll show you some on the field trip. So the reason that we have the soil here, but not here, is that this keeps going up, and that gives it higher potential energy and it erodes faster, so it doesn't show up in the basin or on the upthrown side.
So Carrie has a kind of a comment question. Slip rate, so moved by the earthquake, or is it just slow movement? Might want to look at the fault near Pisgah, north of Big Summit Prairie in Geological mountains.
Yeah, there aren't any creeping faults in Oregon. That would be rather apparent on things like the GPS vectors. And it would show up very clearly, even in satellite photography. Creeping faults like certain segments of the San Andreas or the Hayward Fault or the Calaveras Fault. I actually did a geology video about the Hayward Fault if you visit my YouTube channel, Better Geology. Plug myself there real quick. My point is that the creeping faults are very clear, and we don't see any of those in Oregon, even in the Strawberry Fault. And so that slip rate is, so even though the actual slip, you know, let me draw a little thing. Is it going to let me draw? Yeah, okay. So if we have a rudimentary plot like this, no, it's not what I want. All right, so let's use the axis here of my transect. If the x-axis here is time, and then the y-axis is total slip, you end up getting a shape more like that, where each step is an earthquake. So you end up with total greater displacement over time. But you can also average it out just with a mean. And then the slope of that line is your average millimeters per year slip rate. Does that make sense? Line is too thin. I promise it's there. Great.
I'm curious, because the flip rate does reflect actual earthquakes. Thank you.
Yes, it does.
And she also commented about the Mazama ash layer after the fault that happened. Probably part of the ash mixed in the zone above the Mazama ash layer.
Yes, that's exactly right.
Right.
We see these little sort of soft, fluffy pebbles of the ash all throughout this beige colored ash layer or soil layer above the ash below the most recent earthquake stuff. Textbook example of inclusions.
John Springer is asking, are these faults in any way related to accreted terrains?
That's a very good question. It's something that, that I sit up at 1 a.m. and think about sometimes. So in this map where I have things colored by age, you can see that the Canyon Mountain Complex, this big green blob, is separated from the Strawberry Volcanics here by this fault. This is called the Indian Creek Fault, and the rocks on either side of it differ in age by an order of magnitude. So that's, the orange is 40 million years, the green is nearly 400 million years. And the younger rock is much more fractured and faulted. So this is pretty solid. Its days of active deformation are probably close to done just because it's so dense and cold and so far above the, rocks like to deform in certain ranges of temperature and pressure happiness. And this rock is so far out of that and so solid and old that it is guiding in a way some of the surface expression of these faults in the area. Elsewhere in Oregon, there may very well be places where sort of terrain boundaries are guiding tectonic, strain locations. The Unity Fault Basin, I believe, is one of those Unity Basin faults, rather. There are certain areas where we see something like that, not quite to the extent that you see it elsewhere on the west, just because our slip rates here are so much lower than down in, say, California or Western Washington.
Any other questions there? Carol?
Yeah, you said that the Strawberry Fault is a normal fault
It is.
rather than a thrust fault.
Yes, and you reminded me that I forgot to point out this stereo net. If you've never seen one of these before, this is a way of plotting three-dimensional planes, how they're angled and sloped in 2D space. So this shows that all of these little lines are the way the fault is oriented and how steep is it dipping down into the subsurface. And all of these show that it is dipping to the north, which is also the same direction, or I guess the north side of the fault is the same side that's moving down. And when, that pairing of things, it can only be a normal fault. Yeah, there's one here which is angling to the south. And that's because there's a small antithetic Graben fault over here, which is what I used to approximate the regional strain direction, sort of crudely.
But it does mean things are, thin, stretching and thinning.
I guess so. It doesn't feel like it should be doing that,
Yeah.
but it is.
So the John Day Valley is in a Graben. Over to the draw.
Don't ask that. It's weird. It's a syncline. The beds in the John Day Valley are synclining. The beds to the south are all anticlining. But the John Day Fault sort of skirts both sides of that. And over in the eastern half of the John Day Valley, it's on the south side of that syncline. And on the western half of the John Day Valley, it's on the north side of the syncline. And in some parts, there are faults on both sides. There are parts that more recently have become more Graben-esque. But I would not call the John Day Valley as, fully a feature of a Graben.
Yeah.
It's really quite bizarre.
You've got lots of kudos and thank yous in Zoom here, and I'll
Thank you.
read a message from Wes. He says, Andrew is a huge chip off the block of his dad, Brian, dying. Always striving to follow and discover the actual scientific facts. I'm so glad Andrew is here in Portland pursuing his passion.
Thank you, Wes.
Uh,
Anything else?
All right.
That's wonderful.
Thank you.
Great job.